the order structure. So the structure which has to do with order, which is a order structure where you can put a partial order or a total order. And this is exactly the space which comes from Birkhoff, to the work of Birkhoff, in which you have this school by formal concept analysis in the German tradition. And parallel, this is also very interesting, in France, you have around the École d'études financières et sociales, CAMS, the Center of Analysis and Mathematics of Social Science. You have Marc Bardou, which is doing exactly the same. So two kind of perspectives, I would say, schools about the same object, in which this German tradition has again the flavor of a mathematical tradition, because the starting point in Ville was really how to understand the diatonal space by using order structure, lattice theory. And okay, so I skip these formalities, but as you see here, you are coming back to the tomnets, but in a way which is very different, because you are in the just-tuned space. You have no torques anymore. The space is really infinite, and this has been integrated into a software which is currently developed at Dresden University, Mutabor. This is very much he was young, the time in Darmstadt. At the beginning, the software was introduced in Darmstadt, where Rudolf Wille was living, and now it's developed by Bernard Gartner and his school and mathematics department of Dresden University. So again, this was to show you that there is also this open research axis. We are working at the moment with some master and doctoral students, how to understand this same geometric representation, but using order structure, using lattices. And what is interesting is that there is also a paradigm which has to do with topology, which is very close, which is called the Q analysis, which is close to lattice theory. Every time you have a binary table of relations like this, you can say that these are the object and these are the attribute. And then you can, for example, put here the attribute and the objects as a point, and the attribute if the attribute is shared by the object. Or in the dual way, you can put the point, the attribute, and the surfaces here of your topological structure will become the objects. And this is kind of duality between objects and relations, which is also very interesting from an epistemological point of view. So every time you have a binary table, you can associate a lattice, but also a topological structure, which is a simplicial complex, and how to understand how can you understand, for example, a lattices by using the associated simplicial complex and vice versa. So this is the object of a paper which has been done with a student who worked together in the music representation team. Actually is under reviewing at the moment, and in which we show that some interesting new results. The lattice cannot be fully reconstructed by the simplicial complex that you can associate. So you cannot use the simplicial complexes to reconstruct your lattices. You cannot use the lattice to reconstruct your simplicial complex, but there is an interesting point, which is that the lattice allows to determine the homotopy type of the simplicial complex. So all the invariants are coded somewhere of the invariants of the simplicial complex are coded in the lattice structure. Okay, and why we are interested in simplicial complexes? Because, as I said, the tomnet is a possible way to represent musical structure. It is a space which is given, and then you can see how a piece moves in the space. But you can also think differently, have a piece, and try to build exactly the space which is generated by the piece. So you have Beethoven, you have Chopin, you are making your special computing tool working, and then you reduce because you are just interested in the chord progression, for example, this way, and you end up with a strange and very complex simplicia complex. Sorry for the use of language, a very complicated structure, which is in this case, which is multidimensional, and then you are kind of looking how the composer moved into this space. So this is the space generated by the piece. It's a very different approach from the previous one, in which you had your space, the tonalets, and then you were looking for how a piece moves into a given space. Now the piece generates its proper space, and then we are looking how the composer is moving within the space generated by the piece. And the idea is that these, I show you with the hexachord how you can associate this simplicia complex to the. So if we take the Chopin here. Okay, you have not only the circular representation, but you also have the complex here of the piece. This very complicated multidimensional object, which, as it is, actually this turned out to be a Hamiltonian path. So it's going through all these triangles, which are the chords, in a way which is, again, very similar to the smooth progressions I was doing in my songs, because every time you have two elements which are just kept invariant, and then move one which moves, which is simply I mean, you can see you don't need this, to understand this progression, which is just, a chromatic progression. Okay, but it was interesting to keep this as a kind of general approach in order to say we have a piece of music, we have the spatial computing tool, and we have the space which is generated by the music. And why this? Because maybe at the end we can have a topological signature of a given piece. This is a dream. Because a specific trajectory in the complex, in the simplicia complex, gives you kind of unicity of the piece. So each piece could be maybe is a utopic perspective, but could be characterized in a unique way. In this by looking at the specific trajectory in the complex, in the simplicia complex, which is generated by the piece. Okay, you see? So. Just to give some final examples, why to be interested in this trajectory? Because let's see what happens if you are taking a Bach chorale. It's very general style. Okay, yeah, we are in the right space, which is 3/4/5. 3/4/7, 3/4/5, and the same is the tonal piece, the tonal space. Then we change the space, we go to a more exotic space. So we transform this time. I think it's doesn't need to be really explained. Here we have a space in which the pentatonic scale is playing a major role comparison to this one. So we kind of Chinoisized, China-ized Bach. Okay, this could be taken as a joke, but actually it's very deep, because if you are interested in structuralism, and I think Stefan also is very interested, we had many discussions about the role of structuralism and the possible genealogy of structuralism in mathematics and music. Actually, there is an interesting conversation by Levi-Strauss with writer Eric Bohr that I translated quickly in English, so my translations don't pay too much attention to the details, but the idea is that the notion of transformations, which is very central in the structuralistic in structuralism in the 60s, actually comes from, according to what Levi-Strauss says, to this work by Darcy Thompson, which has to do with morphological properties. So there is a kind of tension between the morphological genealogy of the structuralism and the mathematical genealogy, which goes back to Klein, to all this group theory that I show you applied to music. And so, for example, the different species of fishes are just different instantiation of a kind of cell, of a kind of path, or let's say a kernel, which is kind of injected into different geometrical space. So in order to differentiate, for example, these two fishes, you have to look at the space in which the fish is described. And this is also very clearly connected with Dürer treatise of human proportions, in which he's kind of playing with the underground, so the space in which the object is described. And I find this is very in tune, very kind of compatible with what we were saying. You have a piece, and actually the style of the piece is something which has to do with the space in which you are putting your piece. So if you're now interested in Beatles, you can try to start with Etude, for example, and to do what happens if you are putting the pentatonic space, like we have done with Bach. The result is not so interesting, I found, but gives you an idea of. Trajectory transformations, they can be seen as isomorphism from a super space to a different from a given space to a different given space. And then you come back with so you obtain traditional musical transformation like a chromatic transposition, chromatic inversion, modal transposition, modal inversions, but actually you have a lot of different musical transformations that you cannot explain, that you have no name simply to describe, and which are completely described in terms of the underlying geometrical space in which you are kind of transforming your piece. So you don't need to change your space. You can also have the same space, and you can look at automorphism. So transformation of the trajectory within a given space, and you have, in this case, very interesting results, which are what I call the M transformation, M like Mahler. You know, if you have how to transform a lullaby into a symphony. So major, minor. So the minor approximations, which is also something that you can do in audio processing. From major to minor, and again, these are operations which I found particularly musically logic. How to go from now in the case of etude, if you have a F major chord, what happens if you are doing a rotation? You have your piece and you rotate your trajectory. So every F major chord becomes a C minor. So, and also the melodic interval. So becomes okay. F major becomes a C minor chord, and maybe we can end with this. I can try to let the system play, so this hexachord playing the transformed version, you know, and then and we just accompany. If you let me do that, this will be the end. So etude. Trying to see if I can do the right one. Okay, this is the right one. So actually, at this moment, the system is very tight and normally it stops working. So I will then comes back again. So I will go on and we see if it goes until the end or not.